Let us see the topic stereochemistry. First we see what is isomerism. Organic compound with the same molecular formula but different structures are called isomers. Isomers differ in their physical and chemical properties. For example, molecular formula C2H6O has two isomers possible: CS3CH2OH, ethanol or ethyl alcohol. Second one is CS3OCS3, dimethyl ether. The physical and chemical properties of these two isomers are totally different. Let us see the classification of isomerism. Isomerism can be classified into structural isomerism and stereoisomerism. Structural isomerism is due to difference in bonding pattern, whereas stereoisomerism is due to difference in arrangement of bonds in space. Structural isomerism can be further divided into chain isomerism, position isomerism, functional group isomerism, and metamerism. We will see one by one later. Stereoisomerism can be divided into configurational isomerism and conformational isomerism. Conformational isomerism is somewhat unstable, whereas configurational isomerism is somewhat stable. For example, example for conformational isomerism is eclipsed and staggered forms of ethane. Eclipsed form can easily convert into staggered form by carbon-carbon single bond rotation. So we cannot separate eclipsed form from staggered form in the case of ethane. Similarly, pot and chair forms of cyclohexane are also examples for conformational isomerism. Pot form can easily transform into chair form by carbon-carbon single bond rotation in ring. Let us see configurational isomerism. Configurational isomers are somewhat stable. We can separate each isomers. Configurational isomerism can be divided into optical isomerism and geometrical isomerism. Optical isomerism is due to presence of asymmetric centers or asymmetric atoms like asymmetric carbon atom and asymmetric nitrogen atom, etc. Optical isomerism can be divided into enantiomers and diastereomers. Enantiomers are optical isomers which are related to each other as mirror images, whereas diastereomers are optical isomers which are not related as mirror images. Geometrical isomerism can be divided into two: geometrical isomerism in double bonds and geometrical isomerism in rings. We have heard about the cis and trans isomers. Cis and trans isomerism is possible both in the case of a double bond as well as in rings. Next we see the structural isomerism. Isomers that have different bonding pattern are called structural isomers. First we see chain isomerism. Here isomers differ in the carbon chain or skeleton. For example, C4H10 has two chain isomers possible. First one is a straight chain, normal butane, CS3, CH2, CH2, CH3. Second one is a branched one, 3 carbon atoms in a chain and 1 carbon atom is a branch. So it's called 2-methyl propane is the chain isomerism of so these two are chain isomers. Butane and 2-methyl propane are chain isomers of C4H10. Next we see C5H12. C5H12 has 3 chain isomers possible. First one is a straight chain, CS3, CH2, 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 CS3, pentane, and second one, 4 carbon atoms in a chain and 1 is a branch, the 2-methyl butane, and another one, 3 carbon atoms in a chain and 2 carbon atoms form branches, 2,2-dimethyl propane. So pentane, 2-methyl butane and 2,2-dimethyl propane are chain isomers of C5H12. Next we see position isomerism. Here isomers differ in the position of attachment to functional group. For example, in C3H7Cl, the position of the functional group chlorine can be at C1 or C2. C3H7 means 3 carbon atoms in a chain, and chlorine can be at one end, 1 chloropropane, and the chlorine comes at the middle of the chain. It's called 2 chloropropane. The numbering can be from 1 and 1, 2, 3. So 2 methyl propane. These two compounds are position isomers, because position of attachment of the functional group chlorine is at a different position. One is at position 1 and position 2. Next one, C4H8. The formula implies C4H8 implies the presence of a double bond. Here the position of the double bond can be at a terminal at one end of the chain, or can be at the middle of the chain. So 1 butene and 2 butene are examples for position of isomers. Here the position of the double bond is different. In 1 butene, the position is at one terminal position, and 2 butene, this is a middle position. Next isomerism is functional group isomerism. Here isomers differ in the type of functional group. For example, in C2H5H6O, the possible functional groups are OH, alcohol, and ether, CS3CH2OH, ethanol, and dimethyl ether. These two compounds are examples for functional group. Here the isomerism, here the functional group is OH, here the functional group is ether. Similarly, C3H6, the formula implies the presence of a double bond or a ring. So two possibilities are there with this formula. One is double bond and one is ring. So propanene, and another formula is cyclopropane. Here the functional group is double bond, and here the non-functional group is there. So these two compounds can be regarded as functional group isomers, because here the functional group is double bond, here the functional group is the ring, can be regarded as another functional group. Next is tautomerism. It is a special type of functional group isomerism in which isomers are rapidly interchangeable and maintains a dynamic equilibrium. For example, hydrogen cyanide HCl is rapidly converted to hydrogen isocyanide HNC by rapid exchange of hydrogen atom between polyvalent carbon and nitrogen atoms. Here hydrogen HCl, the hydrogen atom is attached to carbon, whereas in HNC the hydrogen atom is attached to nitrogen atom. This hydrogen atom is transferred into the nitrogen atom, so it becomes HNC. So this is a type of tautomerism. Another type of tautomerism is keto-enol tautomerism. Here is a special kind of functional group isomerism in which keto form rapidly interchange to enol form by exchange of hydrogen atom between oxygen atom and carbon atom. For example, in ethanol, the hydrogen atom present in the CS3 group can be transferred into oxygen atom, and this process is called keto-enol tautomerism. This hydrogen atom is transferred, and this double bond is transferred into the between carbon atom, so it becomes enol. So keto form is transformed into enol. It's actually, in fact, is aldehyde is transformed into enol. So keto form transformed to enol. Since keto form is more stable, enol form only exists in traces. Next is metamerism. Here isomers differ in the number of carbon atom on either side of the heteroatom. For example, diethyl ether has 2 carbon atoms on each side of heteroatom oxygen. See this example, diethyl ether, 2 carbon atoms on either side of the heteroatom oxygen. Whereas in 1-methoxypropane, here there are 3 carbon atoms on one side of oxygen and 1 carbon atom on the other side of oxygen. These two compounds are isomers. Here isomers different number of carbon atoms on either side of the heteroatom oxygen. Another example in secondary amine, for example, diethylamine. There are 2 carbon atoms on either side of NH group. Whereas in this compound, one side there are 3 carbon atoms of around NH group and another side only 1 carbon atom. So the one diethylamine and N-methyl-propan 1-amine are examples for metamerism.